All right. Well, I want to welcome everyone to this month's Center for Safety, Equity, and Transportation webinar. I'm Kevin Chang at the University of Idaho, and it's my pleasure to welcome Professor Scott Washburn, who joins us from the University of Florida, who's going to be presenting on recent rural highway analysis efforts for the Highway Capacity Manual. Before I turn it over to Scott, let me make a brief introduction. Scott is currently a professor in the Department of Civil and Coastal Engineering at the University of Florida. His areas of expertise include traffic flow theory, traffic operations analysis, traffic simulation, model development, development of traffic analysis and level of service computational methods, and complementary software tools. His primary research efforts are focused on conducting, improving, enhancing traffic analysis methods, those focused on the Highway Capacity Manual and developing better software applications. He's a former member of the Transportation Research Board's Highway Capacity and Quality of Service Committee. And many of you know Scott, along with his co-author, Fred Mannering from the University of South Florida, the authors of a very popular college textbook titled Principles of Highway Engineering and Traffic Analysis. So with that, Scott, we welcome you to Moscow, Idaho, and we'll turn the floor over to you. Thank you.
Thank you very much for that introduction, Kevin, and good morning, everybody. It's my pleasure to be with you here. A little cooler weather. It's about 90 degrees, 90% humidity down in Gainesville, Florida right now. So this is a nice little respite here. And just a little bit more background about myself. I've been at University of Florida since 1999. I've been very active with the Highway Capacity Quality of Service Committee since about 2000. I was a formal committee member, used up all of my allotted years for about 10 years, and otherwise, still maintain a very active presence with the committee. And as Dr. Chang mentioned, a lot of my work is targeted for the Highway Capacity Manual, and that's what I'm going to be talking to you about today. Certainly the range of work that I've done has kind of spanned all the different facility types, freeways and highways and arterials. Today I'm going to focus primarily on highways. I was the principal investigator for a National Cooperative Highway Research Program project that finished a couple of years ago. And with that, there is a new chapter or an updated chapter in the Highway Capacity Manual that reflects the efforts of that work. And I'm currently the principal investigator for another NCHRP project that's looking to essentially extend that work that we did with the previous project. And so I'm going to give you an overview. Mostly the bulk of it will be focused on the project that is completed, and then I'm going to give you a little bit of an update on the current project. So we'll go ahead and dive in. So again, this first project, National Cooperative Highway Research Project, it was number 1765. The title was Improved Analysis of Two-Lane Highway Capacity and Operational Performance. The two-lane highway analysis methodology in the Highway Capacity Manual had largely remained the same since the 1985 edition of the Highway Capacity Manual. There have been a few little tweaks over the years to that. But there were some recognized limitations and gaps in the methodology that the committee recognized needed to be addressed. And while with the methods in the Highway Capacity Manual, we're always trying to base those on as much field data as possible. Two-lane highways obviously are a little more challenging than some other facility types to collect field data. And so it has relied quite a bit on simulation. The simulation tool that was used in the work that was previously in the Highway Capacity Manual was outdated. And so that was part of this project as well, to identify essentially a modern simulation tool that we could use to complement the methods that we were developing now. And so, yeah, I'm going to go ahead and kind of give you an overview of this project. First, I want to recognize the members of the research team. Myself, I was the principal investigator, and Dr. Ahmed Al-Kaizi at Montana State University, Dr. Tapio Lutman, recently retired, formerly was Helsinki University of Technology, now Aalto University in Finland, and Dr. Rick Dowling from Kittleson Associates, a former PhD student of mine, Don Watson, a former PhD student of Dr. Alkazi, Amir Jafari, and Dr. Mike Dixon, who some of you may be familiar with, who was faculty member here, sadly passed away as we were actually working on the proposal for this particular project. So just to give you a little bit more background again here on what we were looking to address with new research on this topic. So the speed flow curves were linear in nature. The slope was not affected by the free flow speed. So again, we didn't feel like the linear relationship was accurate with current field data. Very limited guidance on the base free flow speed. The percent time spent following service measure, very difficult to measure in the field, can be misleading in some cases, kind of depending on the combination of volumes and truck percentages. And the 3-second following headway criterion was certainly very debatable. So we wanted to revisit that topic as well. And there's an average travel speed service measure, and that did not always correlate well with the operational efficiency, again, kind of depending on the combination of volumes and truck percentages. Truck impacts. I think, one thing to look at here is this figure. So those of you that are familiar with the Methods Highway Capacity Manual, familiar with the concept of passenger car equivalents, essentially that's how we deal with the trucks, is we convert trucks to some equivalent number of passenger cars. And what that's doing essentially is inflating our analysis flow rate. And we just have this single speed flow relationship. So that just pushes you further out to the right. The challenge with 2-lane highways is you get more variability in geometry, horizontal curves, vertical curves. And just pushing you further out to the right does not necessarily reflect the speed degradation that you would have for these large trucks and consequently passenger cars that queue up behind the trucks. And there were some other challenges because the PC, the way you calculate, depended on the service measure that you were using, and there was an iterative component to it. And so it was a little bit difficult to work with, and again, didn't always reflect the actual speed reduction that you would have on 2-lane highways. There were some issues with the passing lane calculations and overestimating how much they improved performance on the 2-lane highway. There was a percent no passing zone input that again was a little bit awkward because it didn't take into account how that percentage was spread out along a certain length of 2-lane highway, whether it was 50% is the first half, or it's kind of broken up in several segments. Not a lot of data on capacity. This proved unfortunately to be the case even with the new research, and also not facility oriented. It was essentially segment level analysis methodology, but with an adjustment for passing lanes. In terms of ease of use, there were some things that were a little bit undesirable for users. We had 3 different classifications and different service measures that were being used depending on that classification. And if you were a class 1 or looking at a class 1 facility, you had to go through the calculations for both the travel speed service measure and the percent time spent following. And those of us that have taught this in the classroom, this drove students nuts. You get 2 different analysis flow rates. And why do I have to have 2 different flow rates? And so this was always awkward. It's one thing if you're using the software, but if you're teaching this, which you should be at least initially to the students, it was very awkward. And then several lookup tables with factors, some of them 2-way interpolations, some of them 3-way interpolations. And it's amazing, as much calculus as our students take, I think the 3-way linear interpolation tables they found more challenging than calculus. So the objective of this research to revisit performance measures, potentially revise the service measure, that is the performance measure we're using for level of service. And again, potentially overhaul the complete analysis methodology. Also look at newer modern simulation tools that could be used to be able to help us with the research and also potentially check some of the things that come out of this research. and ultimately develop a new chapter for the HCM, which has been done, and I'll touch upon that a bit later too. Yeah, this project was finished in March 2018, and this is the link. And if anybody would like of course, you can just type in NCHRP Project 1765 in your browser, and it should take you to this link. But Dr. Chang can probably get you the link later if you would like, and you can download the report. It's all in PDF format. Just touch real briefly, we had some field data, and we had some state DOTs that were very generous and helped us, because anybody that's worked on these NCHRP projects know, even though there's several $100,000 of budget, they're always underfunded. So you're always looking for help in some form or another. And so we had some state DOTs that helped us out and contributed some field data, so Oregon, Montana. So we had good presence here from the Pacific Northwest, Idaho, North Carolina out east, and then California. We had one site, particularly that site was selected because it had very high flow rates. We were trying to look at potential capacity level flow rates with that site. And these were the locations. We'll just kind of skip through that. Had a large volume of data, of course, and to help us with that, we worked on a software tool to process the data to help us identify, let's say, speed flow relationships, vehicle speed distributions, any number of different things that we were looking at. And if anybody's interested in a software tool, they can contact me. Basically, it reads in different formats for point detection, whether it's loop detectors or pneumatic tubes or something like that. And we can always adjust it if you have a particular format. Anyway, so this was very helpful in making our data processing and analysis more efficient. But it's something I make freely available to anybody that wants it. So again, we could generate some different plots, this speed flow relationship that you're seeing here. I don't think the software itself is on the GitHub site, but again, I can supply that to anybody that wants it. But all of the field data that was collected from this project is available online. And you can go to the GitHub site here to get that. Just briefly talk about simulation. Again, there really wasn't much that was available for two-lane highway simulation. I had worked on a project where we implemented into CoreSim. Those of you that may be familiar with the CoreSim simulation tool. That carried over into another simulation tool that basically I started developing now about 10 years ago, 11 years ago. Because I was running into some limitations with CoreSim because of an older software architecture. So I basically decided to write my own. And so I took all that two-lane highway simulation logic from CoreSim, implemented it into what I'm currently calling SwashSim, and also made some upgrades at the same time. So we use that tool, for all the things, we did get a lot of field data. Unfortunately, there's so much variety with the different scenarios we wanted to look at for two-lane highways. You just can't get it all without, maybe a multi-million-dollar budget from the field data. So we had to supplement that with simulation. We did do calibration with the tool, for the tool with the field data that we collected. And so we relied on this largely for the simulation. There was another tool I coordinated with the folks at Caliper company that produces Transmodeler. And they were in the process of also trying to implement two-lane highway modeling. And so we kind of use this as a double check against our results as well with the SwashSim tool. And if anybody's interested in SwashSim, you can get some more information at the GitHub link there, but you'll just need to send me an email if you want the software itself. I can send you the install. I make it, again, freely available. Transmodeler, they charge for that, but that's the link to learn more about it there. So let me give you an overview here of the analysis methodologies, the concepts behind the analysis methodology. So we have three different segment types now. We've got the passing constrained. So that's where you've got the solid yellow lines you can't pass in the oncoming lane, just a two-lane cross section. passing zone. So now you've got the dashed yellow line and you can pass in the oncoming lane, or a passing lane. So just a short section of additional lane to accommodate breaking up platoons due to slow moving vehicles. And so we no longer have the % no passing zones input, because you would just set this up explicitly as this segment has passing or does not have passing and so on. And again, explicitly accounts for the length of passing zones. And you can now string together a series of contiguous segments and essentially make a facility level analysis. Treatment of trucks. So this is an area where we're deviating a little bit from the highway capacity manual, at least historically. We had quite a bit of discussion within the committee, but we got buy-in from the committee. We don't use the PC. There's no passenger car equivalent concept here. It's explicitly using percentage of trucks. And what we did was we looked at these three different classes of trucks: the single unit truck, the class 8 and the class 9. The class 8 and 9 are essentially tractor trailers, just whether it's a day cab or a long haul cab. And for terrain now, we have 5 different classifications. So depending on the length of the grade and the percentage of the grade, upgrade or downgrade, you would classify it as 1 through 5. So 1 essentially is not much impact to truck speeds. 5 is very significant. They're probably going to be crawl speed going up grades, or crawl speed potentially going down grades because they're trying to avoid the runaway truck phenomenon. And we're also accommodating some horizontal curvature, which we did not have as part of the previous analysis methodology. So again, there's 5 different classifications for horizontal terrain based on the radius of curvature and the super elevation. So the speed flow relationship looks a little bit like what you see there on the left. So it's not a perfectly linear relationship, although with this particular curve, it looks mostly linear, but depending again on percentage of trucks, for example, you might get something that looks quite a bit more non-linear. But certainly, in those first few hundred vehicles per hour, you get a pretty good drop in speed. And then, yeah, it kind of starts to taper off. But again, depending on the percentage of curves, percentage of trucks, those curves can look quite a bit different. So you don't just necessarily have this single curve. And then again, depending on the PCEs, it just pushes you out further to the right. And in the passing lane segment, it looks a little bit more like what you see with a multi-lane highway, as you would expect with 2 lanes. People can change lanes to pass slower vehicles. And then this is the relationship for percent followers. We did quite a bit of work to look at how you determine follower status, and certainly can be a little bit complicated. And in the end, we decided, for the sake of the highway capacity manual, to simplify and find a number that fit well with all this other work that you might go through, these other calculations to identify whether a vehicle really should be considered as a follower. And just came up with this 2.5 second headway. There's a lot more background. So that additional process that we went through is not reflected in the chapter, of course, in the HCM, but if you're interested in that, you get the original research report, and it talks about the different things that we looked at in trying to identify the follower status. But in the end, we went with this 2.5 second headway, which gets us in the ballpark most of the time. And ultimately, then you're going to calculate follower density, which is the new service measure, follower density. So it's just taking density, flow rate divided by average speed, times the percentage of followers. That's an example of what that relationship looks like, the flow rate versus follower density. Previously, we had these 3 different classes, and each one had different service measures. While we just have the single service measure, follower density, we do have 2 different sets of thresholds. So we're still trying to be sensitive to the lower speed highway, maybe goes through a small town, you get a reduction in speed limit, where people are maybe not quite as concerned about following. And so those thresholds are a little bit higher. You can see the numbers in the right column are all a little bit higher than the numbers in the left column. So that's to sort of reflect a reduced sensitivity to following in a lower speed environment. Capacity, so we did have difficulty finding sites with high flow rates, and this has always been a challenge. Agencies have a tendency to upgrade to multi-lane cross section when the VC, the volume to capacity ratio, is still not that high, just because people perceive conditions to be quite poor, even at moderate levels of demand to capacity. So it is hard to find a 2-lane highway that's still out there that's operating with very high flow rates. We had a couple sites. We had the California site, we had a site in North Carolina, and they were in the same ballpark as what the HCM currently has, 17 to 1800 passenger cars per hour. We did not have enough additional evidence to change that, so we left that as is. We did look at passing lanes. This was largely a simulation exercise, however, and you can have a reduction in capacity, at least via simulation, but in conversations with some folks in Europe, where these 2+1, I'll touch upon that again a little bit later, these 2+1 installations are common, but when you have passing lane and then you drop it back down to a single lane under high flow rates, you can get quite a bit of turbulence at that merge point. And that can lead to a reduction in capacity. So we were hearing from folks in Europe, sometimes they have these giant festivals, and where they have the 2+1 or passing lane, they'll actually close the additional lane because they found that becomes more problematic under the high flow rate. So we do have some reductions depending on the percentage of heavy vehicles in the vertical classification to capacity for passing lane configuration. So real quickly, the steps that you go through. Actually, I think I'm going to kind of skip through this. So if you're interested later, you can slow down the video and look at it. But again, these are all outlined in the HCM chapter as well. But as we have with every HCM methodology, we outline the sequence of steps you go through to do the analysis. And this was what I was mentioning before, the 2+1. So this is a continuous 3-lane cross section where you just get an alternation of the passing lanes. The passing lane is always on the inside in the middle, and it just continuously changes direction. And so you typically have like a 2-kilometer length of passing lane, and then you have a little clearance zone. So you try and avoid accidents in between. And in these installations, then of course you do not allow passing the oncoming lane. And so this type of configuration agencies really started to turn to because of safety issues of passing the oncoming lane. So sometimes they are barrier separated, sometimes they're not. We found different countries felt differently about that. Like barriers generally aren't friendly to vehicles, but particularly motorcyclists. So some countries were more sensitive to that than others. So we've never had anything before in the HCM about these 2+1. So it's not comprehensive yet, but we have a small section about 2+1. So US transportation agencies are kind of interested in exploring. This gives them a starting point for that. And yeah, so there's a couple of calculations in there to look at how that type of configuration may improve performance over a typical 2-lane cross section. So real quickly, a summary of this. We did offer a little bit more guidance on base free flow speed. It's simply now a function of the posted speed limit. Unfortunately, with all the field sites we had, I think they were all posted 55, or maybe all but one. In the future, we'd like to get more data from sites with more variety in the posted speed limit. So right now, I think the base free flow speed is just 14% higher than that posted speed limit. But again, when we did the data analysis, it was originally all relative to just 55 miles an hour. We feel that the new speed flow relationship is more realistic with the current field data that we saw. Eliminated the percent time spent following measure, added a percent followers measure. Now we just have a single service measure, but there's 2 different sets of LOS thresholds, and the follower threshold, which previously was 3 seconds, is now 2.5. Again, no PCEs, everything's done in units of vehicles per hour, so there's no conversion to passenger cars per hour. There's some sensitivity now to horizontal curvature. Another thing is, with the previous methodology, essentially those calculations were on a link basis or segment basis. Now, those calculations are specific to the endpoint of the segment. So if an agency wanted to check the calculation from the HCM, they could go out in the field, if they have loop detectors, great, or put down some pneumatic tubes, get some point measures and compare that to the estimates from this methodology. Again, we've got some initial material for the 2+1 configuration. We can accommodate the facility level analysis, and these results are consistent now with what we're seeing from modern simulation tools. On the ease of use, so again, this was something that we were trying to consider in this project, is just to make this methodology a little bit easier to use. There are no tables that require interpolation. There are quite a few lookup tables, but those are specific usually to, say, vertical class. But once you've identified is it 1, 2, 3, 4, or 5, you just get all your coefficients for the equations from that table. There's no interpolation involved. Again, not having to deal with converting from vehicles per hour to passenger cars per hour, single service measure, no percent passing zones input, and eliminating the PTSF measure, which is very difficult, if not impossible, to measure in the field. Again, there's SwashSim, there's Transmodeler, which should give you pretty good results. We think realistic results with the field, what you would observe in the field for simulation. And I think now there's some other tools, the eSIMs, the AIMSIMs, and so on. I noticed that the paper that I did with a student about implementing the 2-lane highway simulation modeling into CoreSim has become extremely popular in the last couple of years. So I think it may be some of these other simulation tool vendors that are looking at that. And so I suspect there's some similarity now in how 2-lane highways are simulated in those tools with how they are in SwashSim. So the chapter was formally adopted by the Highway Capacity Quality Service Committee at the January 2019 meeting in Washington, D.C., the TRB meeting. And then an electronic version of the chapter was released on this hcmvolume4.org and basically a year later. And now it's included in the print, although actually I'm not entirely sure if the print edition has hit the streets. But there is an electronic version now of the HCM 7th edition, which was released earlier this year. So you can get the new analysis methodology. I'm not actually sure if the pre-release version is still on the HCM Volume 4. It might be, but certainly you can get the full official final release version now in the 7th edition of the HCM. And that analysis methodology is included in software that I make available freely called HCM Calc. More information about it's on this GitHub site. And so if you want to experiment with that, send me an email, I'll send you the software. All right, so let me just give you a little bit of an overview now of the current project that we have going on, this NCHRP 08-135, called Reliability and Quality of Service Evaluation Methods for Rural Highways. And this is our research team here. Again, I'm the principal investigator. Dr. Alkaisi from Montana State University is on the team. And then we have Kittleson Associates, Bastian Shorter is leading that part of it. And Anna Moreno, who's with Technical University of Munich in a postdoctoral research position. And this project is now kind of taking what we've done before and trying to take it to the next level. So the previous project was focused exclusively on 2-lane highways. Now what we're trying to do is expand that to highways, but a little more specifically rural highways. And what we want to be able to do, so in the HCM, we've got a facility methodology for freeways, arterials, and two-lane highways now. But we don't have a way to connect multi-lane highways to two-lane highways to the occasional intersection, signalized, roundabout, always stop control. And so this project now is trying to develop that rural highway facility methodology. Also trying to look at reliability. Reliability has become a focus now in the HCM. We have a reliability methodology for freeways and arterial streets, where we're looking at demand variability, say over a year's time, looking at weather events, looking at incident events, and how that leads to variability in travel times. The challenge, let me see, I might have that here in a future slide. So let me come back to the reliability component in just a moment. But yeah, there's some different challenges here with the rural highways versus freeways versus arterial streets. One, much longer distances we're usually looking at, more variability in the geometry, horizontal, vertical alignment, and you get some variability in these different cross sections. Whereas there's quite a bit of similarity in a freeway facility from one segment to the next. It's really more, does it have an on-ramp? Does it have an off-ramp? And even with arterials, again, quite a bit of consistency in the cross section along the length of the arterial. The rural highways often serve quite a significant percentage of recreational traffic, particularly on weekends. They even serve some bicycle traffic. So the objectives of this project: develop guidance for segmenting a facility. Again, how do we identify this is multi-lane, this is two-lane, this is an intersection, so on, but a little bit more than that I'll touch on in a second. Develop a level service methodology for automobiles. Develop a reliability analysis methodology for automobiles. Develop a guidebook for the users, and identify research and analysis needs for the bicycle mode on rural highways. So the segmentation, some of it is probably pretty straightforward. We're going from 4 lanes to 2 lanes. Okay, got a multi-lane, we've got a 2-lane. It gets a little bit more complicated where you have intersections, because intersections often are just considered as points, but they're not just points. They certainly have an effect on operations a little bit upstream, a little bit downstream. So we're trying to identify, what are those influence areas, and how does, say, signal timing and the traffic characteristics and so on affect how much influence that intersection has upstream and downstream. And then you would adjust the lengths of those adjoining segments accordingly. And the guidance on when you analyze, say, a stretch of arterial roadway with the urban street analysis methodology in the HCM is somewhat generalized. We're looking to try and make that a little bit more comprehensive. So when would you use that urban streets methodology versus, say, just using an isolated signalized intersection analysis methodology combined with a upstream 2-lane segment or multi-lane segment or downstream? And so with that, again, we're trying to look at a number of factors. Certainly signal coordination might play into that, possibly demand volumes, driveway presence, roadside activity like parallel parking, things like that. So just trying to develop a little more comprehensive guidance, because we have heard from agencies that they would like some better guidance on when they should be using the urban streets methodology. And that, again, would be applicable when you're going to, even though we're talking rural highways, you go through these small towns and you might get a series of few intersections that would operate more like an arterial street. So again, when we think about freeways, the service measure is density, whether it's a basic segment, whether it's an on-ramp, off-ramp segment, weaving segment, it's the same service measure throughout. Likewise, with an arterial, delay is the service measure. Here, it's a little more complicated. 2-lane highways, we're using follower density. Multi-lane highways, density. Intersections use delay. So how do we come up with an overall facility level service methodology with somewhat disparate service measures? So that's something we're needing to figure out. On the reliability aspect, so there's been a lot of back and forth on this with the panel. Again, the way that it's been treated in the HCM is we want to look at usually a year-long duration of traffic demands and weather events and incident events, possibly even construction zone information, and develop a distribution ultimately of travel time. These kind of data are a little harder to come by for rural facilities right now. Usually the data, say the demand volume data collection points are much more sparse than an urban freeway situation. Weather data collection, maybe again, more sparse in these rural areas. Incident data collection, there's traffic management centers to track incidents on urban corridors, and they don't see it directly. People call in and report it, but a lot of incidents on rural routes go unreported. So we're probably not going to end up with something that looks like the travel time reliability analysis methodology we have right now for freeways and arterials. What we're trying to do right now is look at how we can use existing probe vehicle data, such as INRIX data, HERE data, something like that, to at least help kind of identify hotspots spatially, temporally. Is there a certain section of this highway that appears that it might be problematic, or certain time of year, everybody getting ready to, people traveling up to the ski resort or something like that. But it's not going to be, say, as microscopic as, oh yeah, it's this 4 to 5 p.m. time period that's the real challenge here, or it's this one intersection has an issue. We just really don't have the data to get at that. But we're going to also try and kind of lay out, here's where we need to go in the future to try and get to that. So hopefully some useful guidance for future projects when the data do become available to develop a travel time reliability analysis methodology that may be more similar to what you see now for freeways and arterials. And we're putting together computational engines. So again, this is being built within HCM Calc, where again, you can have this series of segments, multi-lane highway, 2-lane highway, different intersection types, and so on. And this will be available when the project is over. And again, we're developing a guidebook. So we're going to have several example problems and show, have a step-by-step process for how you go about analyzing that to help people when they want to do their rural highway analysis. And we're planning to do it in a little more dynamic format, host it on GitHub. Certainly it could be printed to PDF, but the hope is this will be easier to update and people can easily go in and identify, oh, you've got a typo here, or the wording's awkward here, or things like that, but a lot easier to maintain and update ultimately. And there's a bicycle component to this, so we're not going to be developing a bicycle level service methodology. There is a current one, but it's recognized it does have quite a few limitations. Agencies are looking at some other analysis methodologies that are out there for bicycles. So we're trying to figure out from both practitioners and avid cyclists on rural highways, where do we need to go? Where do we need more research? Where do we have gaps and limitations in the existing HCM analysis methodology? And identify that again for a future project. Okay. We're doing time, so I will end it there. And if we have any questions from the in-person or the online audience, I'll be happy to entertain those.
So for those that are on Zoom, we encourage you to use the chat pod if you have any questions. And I've got the Zoom link on my left, on my surface here, so I will be monitoring the chat. And if there's any questions from us in the room.
Yeah, I will ask a question about some alternative data for that can be used because the Federal Highway Administration invested lots of money for USDOT for the naturalistic driving study with, I think, some significant portion of this data were on 2-lane rural highway. Have you looked in the new project in terms of such data can be utilized or at least incorporated?
Yeah, good question. We did look into the naturalistic driving data a little bit. We honestly kind of got scared away because of the administrative requirements. We were a little bit worried about the timeline, so there's a process to go through to get permission to use the data and so forth. But you're right, it looked like there was a fair amount that would be available on these rural highways. But we were a little concerned with the time it would take to get all the permissions to use it and the time to process it. Maybe in the future, that's something definitely to look at. But we did decide to pass on that for now. The other thing we decided was we were going to try and rely on data that's just readily available right now to state DOTs, so both from the operations and even the reliability. So that's why, for example, we're looking at the INRIX. So RIDIS is maintaining that. So, we're only using what we can get from within the RIDIS database system. And in particular, we are focused on the XD. So we decided, so the XD is the higher definition, you get smaller segments. But even those are still about 0.6 miles in length. There's only, I'm trying to remember now, like 15 states that have the XD data, but there are a few, or quite a few, I think, that are moving towards trying to get the XD set up for their state. But the non-XD, we kind of decided is not very useful at all for what we were trying to do. But our hope is, the XD will become more readily available. And then again, using these point counts and so forth that DOTs have, like through the MS2 database system. But I think, there probably is a lot we could also eventually get from that naturalistic driving data, but maybe in a future project.
Thank you.
Mm-hmm.
Scott, I have a question. You mentioned segmentation earlier, and I'm just wondering, are there practical limits to, so let's say hypothetically you have one facility that's 20 miles long, you have another facility that's 40 miles long. Is there guidance to say you should break it into, the longer facility, you should break it into smaller chunks? Is there a length at which this methodology starts to kind of fall apart? And can you provide a little bit of insight on that?
Another really good question, and I don't have the answer to that yet, but that is something, yes, we've been talking about. The thing, for example, one thing you always have to be careful of is if you have a service measure that is susceptible to significant changes just by, let's say like you said, we've got this 20-mile stretch. There's a lot of, what we're calling these hot spots, slow down locations and so on. Maybe over that stretch, the level of service isn't very good. And then you've got this long, again, maybe 20-mile multi-lane or whatever it is, but at that point, most of the traffic is gone and everything's running at free flow speed. Well, now you just add that to that, and then, you essentially wash it all out. You wash out the hot spots you had here, because now that you've added the same length of really good conditions, it's sort of masking the poor conditions. And so, that's something we're trying to be careful of as we look at this facility level methodology, is how do you, who knows exactly how people are going to use this, but sometimes, unfortunately, people play games with the analysis methodologies. That's always been a challenge with the step nature of the level of service. It's, we're just a second of delay into level service C. So let's see what we can tweak just a little bit, shave a second off. Well, now we're level service B. It's not, well, you've only changed it a second, but now it's a whole level service category better. And so as part of this, we're also trying to make sure that you do call out essentially the hotspots as part of this process. You need to identify, and we're trying to figure out how that can certainly be more explicit in the level of service methodology. So you can't just keep adding on some length of good conditions to essentially hide the poor conditions from some other stretch, but we're still a little bit early in that process, but yeah, thank you for that question, because that's something that definitely needs to be considered.
Very good. Vicki, do you see any, or are there any questions on the chat on your end?
No, and I'm gonna stop recording now.
But yeah, my contact information is there if anybody wants to follow up on anything